Hi guys, so today we'll be learning about logistic regression. Uh, dif- uh, this is another algorithm, machine learning algorithm. Now, so what is logistic regression? So it is a classification algorithm. Despite the name, it is a tool for predictive classification. So like in name, it is written regression, but it is not regression problem. Regression algorithms, it is used for classification problems like predicting classes like diabetes, non-diabetes, male, female, means which have class as 0 and 1. Uh, Now, probability estimations predicts the probability of an instance belonging to specific class. So here we will be predicting the probability, and on the basis of probability, we will be assigning the class. Produce value strictly between 0 to 1. This produce value between 0 and 1. On the basis of that value, we will tell like is it belongs to class 0 or is it belongs to class 1 if it is a binary class problem. And binary classification primarily used for yes, no, or 0, 1 outcomes, or like cases like diabetes, non-diabetes, this type of problems. So linear versus logistic. Linear regression isn't suitable for classification as it predicts value outside of 0 and 1, and logistic regression handle this by mapping prediction, yeah, and decision power. By modeling probability, we can set thresholds and define decision boundaries that separate different categorical groups effectively. So here we will model the probability by setting a threshold value, and this threshold value will be acting as a decision boundary, and on the basis of that decision boundary we will like separate different categorical groups as 0 and 1. So some of the application where it is used is spam filtering, which is in our email apps, medical diagnostics like predicting that is particular man is suffering from this disease or not, credit scoring, assessing if a browser will default on a loan payment on basis of your histories. So this is like application related to this algorithm. Code classification tasks are categorical output. Unlike regression, the target value is discrete. So here the target value is discrete, which means that you have a particular class, fixed particular class. Like you are predicting cat, is the image belongs is of cat or dog. So it is a class one. We can assign cat as class 0 and dog as class 1. So it is a categorical output. Binary classes like standard task involving two class, where there is only two class, we say it as binary class. Probabilistic logic, we calculate the likelihood and then assign a class level. We will study further about this third point, the threshold. So we define the threshold value, and if the probability greater than this, then we say that it is uh, there is a case where your probability is between you will get probability between 0 to 1. So we will be like there take a case where we are as we are defining our threshold at 0.5. So below 0.5 we say that it belongs to class 0, and above 0.5 and 0.5 we say it as it belongs to class 1. So the linear score Z. So the first step in logistic regression is computing a linear combination of input features identical to linear regression. So here you can see that we are doing same as what we were doing in linear regression. This is called as linear score, which we compute by multiplying weight matrix with the input features. So we get this equation. So the linear score act as a law evidence that we then pass through a nonlinear activation function. Now the value which we will be getting from here, we will be passing it through a nonlinear activation function. So let's take a nonlinear activation function which is sigmoid function. So the equation of sigmoid function is 1 by 1 plus e to the power minus z. Now why we are using sigmoid? Because it shrinks the value between 0 and 1. So the logistic sigmoid function maps any real value number in the range 0 to 1, and this is the curve, sigmoid curve, where the as-shaped curve is essential for compressing a linear score into probability. You can see this score is between 0 to 1. Always for every real number the value will be between 0 to 1. Now mathematical properties, range. Yeah, you have seen its range is between 0 to 1, and monotonicity, the function is always increasing as z increases. You can see here as as gen increases, it is increasing. Now differentiability, smooth curve allow for gradient based optimization as it is smooth, so you can differentiate. Symmetry at z is equal to 0, the output is exactly 0.5. So you can see here, this is the symmetry at z is equal to 0, the output is 0.5. Now model equation. So the value z value, which is w transpose x, we will pass that z value inside sigmoid function, and that value will be between 0 to 1, which we will call as hwx. Now if a probability given y equals to 1 given x, we will call it as hwx. Then probability of y equals to 0 given x will be 1 minus hwx. It's normal, as we can know, we know it through probability. So yeah. Now if z value is greater than or equal to 0, then our hwx value will be greater than or equal to 0.5, as we know it from sigmoid function. Whenever we will put the values greater than or equal to 0, we will get y values or hx value greater than 0.5, and when the value will be less than 0, the value will become less than 0.5. So we will make this 0.5 as our threshold, and the value which after calculating the sigmoid of the value and value, the if the value is 0.5 or greater than that, we will say that it belongs to class 1, and if sigmoid value is less than 0.5, we will say it as it belongs to class 0. The boundary is defined by the plane W transpose X. So this is the boundary. This is the boundary which is actually acting as a decision boundary here. W transpose X. Now there is a concept of odds, which so it is also known. So here it is relative likelihood. So what is odds? Odds equals to probability of predicting y equals to 1 given x upon probability of predicting y equals to 0 given x. This ratio is known as odds. So odds measure the ratio of success probability to the failure failure probability. Okay. Now we will find log odds. Log, how we will just log the value of odds, you will get it as log odds or logics. Taking the natural algorithm of odd transforms our non-linear probability back into the linear function. As this is a non-linear, so when we will be taking log of it, it gets converted again into linear function. It gets so again it is getting converted into linear function, which is W transpose X. Now significance, why we are doing log. So first of all, parameters are linear in the log out space, making it computationally tractable, because here this is a non-linear function. So after taking log, it will become linear, so it will be easy for us to computational purpose, it will be easy. Interpretation, coefficient shows the change in log odds for a unit change in feature x. So we can easily interpret, because whenever there is a unit change in feature x, then we can it shows the change in log odds value, how much change is being done. Other is its links with the Bernoulli distribution outcome to a linear predictor model. If we will see what does it mean here, like assume each trial is a Bernoulli event with probability p. So the probability mass function can be written as sigmoid of W transpose x to the power y. This is z, sigmoid of z, as we know that this is the probability, this whole is the probability, this whole is the probability. So sigmoid of W transpose x to the power y, uh, uh, like if y is a like this is a type of Bernoulli distribution, because there is a, like we can see that here there is a win and a failure type of case. So we can say this is a Bernoulli event. Each trial is a Bernoulli event with probability p. So let's take this is a probability of win to the power y, and this is the probability of failure to the power 1 minus y. So now now we have an independent observation, so we have to multiply each of, because they are independent. So an independent observation, the likelihood is the product of individual probabilities, so we will be multiplying each of them, and then our goal will be to find the parameter w that maximize the likelihood. Now why we want to maximize this likelihood? Because we want that this value should be maximum, like this value should be maximum, because we want that predicting 1 or predicting 0, the likelihood to predict 1 or predict 0 should be maximum. So that's why we want to maximize this likelihood. Now, uh, multiplying small probabilities lead to numerical stability. So we will, after multiply this small probability, it will bring in instability. So we will take log both sides. So after taking log, this y1 will come down, and this 1 minus y1 will also come down, and then they will become y1 log sigma of w transpose xi. This whole term is like new term after taking log. Now, so what will be the loss function? As this we want to maximize it. So if we want to minimize, actually we always try to minimize the loss. So to make it a loss function, we will take negative both sides. So and then our aim will be to minimize that. So after this, our aim will be to minimize that. Now the binary cross entropy BC measure the distance between the actual class and the predicted probability. If our y equals to 1, if we take y equals to 1 here, y equals to 1, we will get log of itna plus this term will get cancelled. So here this term will remain, but when if you try to minimize it, so this equation will become minus minus, we have taken both side minus, so it minus log of summation w transpose xi will be there. So we can write it as hx also, so it will be minus log of hx. Here it will be minus log of hx. So if this hx, if this hx tends to 0, it means that your model is predicting it as 0, then your loss will go to infinity. It means that your loss is increasing. So, and if this value goes near to 1, and your actual value is also 1, you can see that the loss becomes 0. You can see that it is working as a loss. You can see how this loss is working. Whenever if actual value is 1 and your model predicted as 0, model tends means model is not predicting it as 1, it is predicting the probability as 0.1, 0.2, which is near to 0, then you can see that loss will also like loss will also tends to infinity. And if your model predict it as 1, then you can see that loss will become 0. Same here, also same thing happening. So yes, this is working as a loss function. You can see how it is working as a loss function. Now what this graph is telling you here, this is y equals to 1 and this is y equals to 0. So at uh, when probability is 0, your model is predicting the probability as 0. Here y equals to 1 will have y equals to 1 will be maximum, and y equals to 0 will be near to 0. Because and when you move towards so when you move towards y equals to 1, when you move towards probability equals to 1, your y equals to 0, y equals to 0 increases, and your y equals to 1 decreases. Your y equals to 1 decreases. So every point of time, this tries to balance it. So we have to find the point where the likelihood is maximum. We have to find the exact point where the likelihood is maximum. Uh, as you can see here, like when actual value is like here it is 0.5. So below that's 0.5, if any value will be there, we say that the value is 0, because we say that the value is 0 because you can see that log loss for 0 is less than log loss for 1. As at point 0 you can see that the log loss for 0 is 0, and for this it is infinity. So yes, the value will be 0 because for 1 it is infinity. So you, like, we have to find a point where the maximum likelihood is maximum. Maximum likelihood is maximum. What will be the appropriate point where maximum likelihood will be maximum? Now, so the cost function will be 1 by n, will also divided by 1 by n. The cost is the average of individual loss across all training example. This was like, we have calculated this. Now all losses will sum it and divide upon n. So we will be getting it as the average cost function. I've done it here. The binary cross entropy loss for logistic regression is convex. This is critical because it guarantees that a global minimum exists, and that's gradient descent will find it, unlike deep neural. Yeah, so we will now see how this optimization happen and how the weight is updated. So here also, first you initialize your weight as a random value, then you compute the derivative of your cost function, you put it in this equation same as our linear regression, then you update the weight in the opposite direction of gradient, move weights in the opposite direction of gradient, and repeat the until the change in loss is negligible. Then, like, if the loss becomes stops improving or negligible improvement is being updated, or negligible improvement is being shown by the model, so then we stop, because it is actually um, it is actually using your computational power but not giving much difference. That's why we stop it, because it has converged near to minima. Yeah, it is like how we differentiate it, so we know it. Training consideration, feature scaling, crucial for faster convergence of gradient descent. Yeah, so we should always scale our feature between particular limit like 0 to 1, or the feature should be in particular scale, should be in between a particular scale like 0 to 1. Learning rate, so we have a correct and balanced learning rate for speed and stability. And for conversion monitoring, loss and gradient magnitude, we should always monitor our loss improvement or loss change, so that we can know when to stop the training. So ML pipeline works in such a way that firstly we clean and handle missing values in our data, then we do encoding, selection and scaling, then we fit the logistic model through maximum likelihood estimation, and then we evaluate our model, how is it working. We will read much uh, later in our course, we will be reading much about this evaluation part in deep. So yeah, we have many lectures around this. Now, interpretability. Directly see how features impact probability. This is the advantage of logistic regression. Low compute requirements for training and inference, and works exceptionally well on massive data sets. Limitations: linear constraint. It assumes a linear decision boundary. It cannot solve nonlinear separable problems like XOR without feature engineering. Independence assumption. Assume little to no collinearity between independent variables for optimal performance. As we have seen that we have taken an assumption that all these instances are independent to each other. So that's what it is saying. But in general, it is not true. Now, extending it to the multi-class, as we have only studied about binary class, what will happen if it is a multi-class? So one versus rest. Train one classifier per class. Then so there is a softmax function, which is the generalized form of sigmoid function, which is used for k classes. So softmax function equation is like ex upon summation of ex. Uh, e, sorry, ek upon summation of ek, where k equals to 1 to n, means all classes we have to do. Now this equations give you values between 0 to 1 only, and the class which have the highest probability, you assign that feature, or you assign that instance, that class, which of the class where it has the highest probability. And here we use categorical cross-entropy loss. The lecture summary: logistic regression is probabilistic classification model, uses the sigmoid functions to map linear scores to 0, 1, optimized by minimizing binary cross-entropy loss through gradient descent, serves as a powerful interpretable baseline for ML task. These are the image source. Thank you. In our next lecture, we will be studying about discriminant analysis, like linear discriminant analysis and Fisher discriminant analysis. So yeah, thank you.